Welcome to Eternal Vault, the channel where the universe's most extraordinary mysteries are unveiled and the boundaries of imagination are stretched to their limits. Today we're exploring a phenomenon so extreme, so mind-bending, that it challenges every intuition about matter, weight, and the very structure of reality. Picture an ordinary teaspoon in your hand. Now imagine filling it, not with sugar, salt, or even sand, but with matter from a neutron star, one of the densest objects in the universe outside of black holes. That tiny scoop would weigh 5.5 trillion kilograms, 6 billion tons. To put it in perspective, that's more than the combined mass of the entire human population multiplied tenfold. A weight so intense, it would crush continents if it ever fell to Earth. This is not science fiction. This is reality at the limits of physics. In this video, we will journey from the fiery birth and violent deaths of massive stars to the compression of matter beyond imagination, to the bizarre interiors of neutron stars, and finally to their cosmic role as alchemists of the universe, forging the gold, platinum, and uranium that enrich our world. So buckle up. This is the story of a teaspoon that defies comprehension and the celestial forges that created it. Our story begins with the familiar, our sun. For billions of years it has maintained a delicate balance, a tug-of-war between gravity, trying to crush it inward, and nuclear fusion, pushing outward. In its core, hydrogen atoms collide at incredible speeds, fusing into helium and releasing immense energy that lights the sky and warms our planet. This equilibrium defines the life of all stars. Our sun is stable and long-lived, destined to fade quietly into a white dwarf billions of years from now. Its death will be gentle, leaving behind a glowing ember slowly cooling in the cosmic darkness. But the universe also hosts giants, stars 8, 10, 30 times more massive than the sun. These are the rock stars of the cosmos, brilliant, short-lived, and destined for spectacular destruction. Their lives are a frantic sprint, burning through nuclear fuel millions of times faster than the sun. Inside these giants, fusion progresses in concentric layers like a cosmic onion. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, until iron dominates the core. Iron is different. Unlike previous fusion reactions, fusing iron consumes energy instead of releasing it. At that moment, the star's support column disappears, and gravity, the eternal force pressing inward, finally wins. Within seconds, the core collapses under tremendous pressure, while the outer layers plummet inward at significant fractions of the speed of light. Then, the core rebounds, sending shockwaves outward. The result is a supernova, a cataclysm that can briefly outshine its entire galaxy, scattering elements like carbon, oxygen, and calcium across space, ingredients essential for life. At the heart of the supernova, however, lies the remnant that will become our ultimate cosmic heavyweight, the neutron star. To understand the formation of neutron stars, we must first introduce a remarkable concept: degeneracy pressure, a quantum mechanical effect. This was explored and quantified by Subrahmanyan Chandrasekhar, a pioneering Indian astrophysicist. He calculated that any stellar core exceeding 1.4 solar masses would collapse, as electron degeneracy pressure, the force resisting compression, would be insufficient. Electrons are stubborn particles. Quantum mechanics forbids them from occupying the same state in the same space, so they push back when squeezed. This force can hold up a white dwarf, but in the cores of massive stars, gravity is too strong. Electrons are forced into protons, creating neutrons in a process called electron capture. In a fraction of a second, the core transforms into a dense quantum soup of neutrons, a gigantic atomic nucleus. A teaspoon of this material contains 6 billion tons because almost all the empty space that exists in normal atoms has been eliminated. The neutron star is thus born, matter compressed to its extreme limit. It is a celestial object where physics bends, where everyday intuition fails, and where the building blocks of matter reveal their raw, ultimate form. Neutron stars are more than just dense. They are bizarre worlds beyond imagination. The surface may be just a few meters thick in plasma, but beneath lies a crystalline crust of iron nuclei, billions of times stronger than steel. Any mountain would barely rise a millimeter before gravity flattened it. Going deeper, neutrons escape nuclei, forming a superfluid ocean, flowing without friction. Even stranger is the nuclear pasta layer. Under unimaginable pressures, atomic nuclei deform into bizarre shapes. spaghetti-like strands, lasagna sheets, gnocchi clumps, and Swiss cheese structures. This layer is possibly the strongest material in the universe, resilient against the crushing force of gravity. At the very center, the inner core remains a mystery. Densities may reach 8 times that of atomic nuclei. Here, neutrons may dissolve into quark-gluon plasma, a state of matter only seen in the first moments after the Big Bang. Exotic particles like hyperons may emerge. The inner core is a cosmic laboratory where physicists test the limits of known science. Neutron stars exhibit extreme physics in every dimension. Gravity. Surface gravity is 200 billion times that of Earth. A human would be flattened instantly. The escape velocity is half the speed of light. Rotation. Collapsing stars conserve angular momentum, producing pulsars spinning hundreds of times per second. The fastest known, PSRJ 1748-2446 AD, spins 716 times per second, with equatorial speed nearly a quarter of light speed. Pulsars act as cosmic lighthouses, their beams sweeping across space with metronomic precision. Magnetism. Some neutron stars, magnetars, have magnetic fields trillions of times stronger than Earth's. In 2004, the magnetar SGR 1806-20 released a flare that temporarily affected Earth's ionosphere from 50,000 light-years away. These fields are so strong they could erase all magnetic data on Earth. The universe's most extreme laboratories are also its most beautiful and terrifying. Neutron stars are not only extreme, they are creators. When 2 neutron stars orbit each other, they emit gravitational waves, spiral inward, and collide in a kilonova. This collision is a furnace where the R process occurs. Atomic nuclei capture neutrons rapidly, forming heavy elements like gold, platinum, uranium, and tellurium. The 2017 LIGO-Virgo detection confirmed these predictions. Gravitational waves rippled across space. Telescopes observed the light from the kilonova, and scientists traced the origins of these elements. Every gold wedding ring, every platinum chip in electronics, every uranium atom in reactors, even the iodine in your thyroid, was forged in these violent cosmic events, connecting us directly to neutron stars. Pulsars, first discovered by Jocelyn Bell Burnell in 1967, have provided humanity with more than cosmic curiosity. They serve as precise clocks in the galaxy. Their predictable pulses allow astronomers to map space, test Einstein's theory of general relativity, and even propose a galactic navigation system for future interstellar travel. Pulsars exemplify how neutron stars are not just dense curiosities, they are essential tools for understanding the universe. Magnetars push physics to its breaking point. Starquakes on their crusts release energy greater than the sun emits in 100,000 years. Their magnetic fields distort matter, warp spacetime, and generate bursts of X-rays and gamma rays detectable across galaxies. In essence, neutron stars are laboratories of extreme matter, spinning quantum engines and cosmic furnaces all at once. Neutron stars force us to reconsider our place in the universe. A teaspoon weighing 6 billion tons is a reminder of the scale of nature, the limits of human intuition, and the intricate chain of events that forged our world. The gold in your ring, the uranium powering our plants, even your own atoms, all bear the signature of stellar violence billions of years ago. We are not separate from the universe. We are its products, its witnesses, its inheritors. The study of neutron stars is a testament to global collaboration. Chandrasekhar, India, formulated the Chandrasekhar limit, predicting the collapse of massive stellar cores. Jocelyn Bell Burnell, UK, Northern Ireland, discovered pulsars, opening a new field in astrophysics. LIGO and Virgo, USA and Europe, detected gravitational waves from neutron star mergers, confirming theories of element formation. James Webb Space Telescope, International, observed kilonovae and confirmed heavy element creation in real time. Neutron stars remind us that understanding the universe transcends borders, requiring global curiosity, ingenuity, and collaboration. From a simple teaspoon, we've journeyed to the edge of physics, witnessed the death of massive stars, traveled through layers of nuclear pasta and superfluid neutrons, experienced gravity, spin, and magnetism beyond comprehension, observed cosmic collisions that create gold, platinum, and uranium, connected humanity to the violent yet creative forces of the cosmos. A neutron star is matter's final stand before the abyss of a black hole. It is a monument to extremes, a reminder that the universe is far more violent, creative, and extraordinary than we can imagine. And all of this begins with a single teaspoon, weighing 6 billion tons. If your mind has been as crushed as the core of a neutron star, subscribe to Infinite Archive, hit the bell, and join us as we explore the universe's most mind-bending phenomena. From black holes to neutron stars, from the dawn of galaxies to the edge of space-time, the Archive of Infinity has endless mysteries, and this is just one.